start recording. Today is 12/15/17. Your brains are rested and refreshed and ready to go after your long winter's nap yesterday or whatever happened yesterday. Eggnog, I don't know. So we've talked about ionic compounds, we've talked about covalent compounds, right? For covalent compounds, I'm going to draw a nice simple covalent compound here. That's methane, carbon tetrahydride, big component of cow farts. I very often just reference methane as, hey, look, it's cow fart. Methane, pretty common chemical, very flammable, good stuff. Covalently bonded, meaning those hydrogen and the carbon are sharing electrons. We can represent it with a Lewis structure because the little dashed lines between them mean they're sharing. Their orbitals are actually overlapped. Okay, so I'm going to write covalent. We said we could represent ionic compounds with Lewis dot diagrams because we have things like sodium that's lost an electron and fluorine that's gained an electron, which makes it a fluoride ion. And they're not overlapping, they're not sharing orbitals at all. But we can draw them, we can represent them this way because they're sort of shoulder to shoulder. And that's an ionic compound. Okay, cool. So far, so good. Now, we're going to start to represent, with Lewis dot diagrams, something that is not a compound at all. Polyatomic ions. So what would happen if you had a bunch of atoms that were covalently bonded, that were sharing electrons, and then as a group, they picked up extra electrons, or they lost one electron? So let's take this example. You guys actually drew this, NH3. It's ammonia. It's a compound. It's neutral. So NH3 looks like this. Bop, bop. And then hydrogen, 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 boom, boom, boom. Neutral compound. Same number of protons as electrons. Well, what if you could persuade an ammonium ion to give up one of those electrons? Whoops. And along came a hydrogen with its one little electron, which could slide right into place there. You now have one more proton than you do electron. We can get rid of these two dots. Whoops. And we can represent, easy for me to say, not so much to do apparently. We can represent that with a little dashed line. We now have an ion, which means we have to bracket it. It's got one more proton than it did electron. That's an ammonium ion. Instead of NH3, we now have NH4, 1 plus. Huh. The thing that carries over from, I would say yesterday, but the last day we were together, the big thing that you have to remember is when you draw an ion, whoops, with a Lewis diagram, you have to put that bracket around it, and you have to write the charge. So, the bracket and the charge. That's a big thing to remember when you're doing polyatomic ions. So, a polyatomic ion, as I said, it's just a group of atoms that are covalently bonded, and that as a group has either gained or lost electrons. And at this level of chemistry, we don't need to worry about why they lose or gain specific ones or anything else, because at this level of chemistry, you don't have to predict that. All you ever have to do right now is be able to represent them, and in the next chapter, you're going to start memorizing what they are. So I don't think it's useful to memorize them all, so I give you a chart and you just start using them extensively. And once you've used them all about 1.5 million times, you'll just know them. You won't even have to look them up anymore. It's kind of magical. So let's practice drawing these, because here's the nice thing about the Gooch math. And I will say these are the things that gave me the most fits when I was learning to do Lewis structures. The Gooch math on these means that you can predict all the bonds. You're not guessing. You're not moving electrons around. You're not adding miscellaneous random electrons. You just know how to do it because of the Gooch math. So let's go ahead and do, oh, what the heck. Let's do the phosphate ion, Po4, 3-. Okay, so we're doing the same thing we've always done. We're starting off by listing the number of valence electrons. That's the number of electrons this is coming in with. So we have 1 phosphorus, 4 oxygens. How many valence electrons does phosphorus have? You got to have your periodic table out. Group 15? 5. So this gives us 5. Oxygen has 6. 6 times 4, 24. Here's the catch. This is the catch. It's got a 3- charge. Does it have extra electrons or did it give up electrons? It's got extra electrons. How many extra electrons? 3. So we have to put in here plus 3 electrons. So that's 3. So this is coming in then with 29, 32 valence electrons. How many octet would it like to have? Well, phosphorus and oxygen are both octet conformers. 8. 8 times 1 times 4, we get 40. Okay. 40 octet. So octet minus valence equals the number that are shared. 8 shared. So far, so good? Okay. Number of shared divided by 2. 4 bonds. I'm going to shrink some stuff here. Now, what goes in the center? Least electronegative or carbon. And if you look at your periodic table, electronegativity tends to increase towards group 18. Phosphorus would be less electronegative than oxygen. Here's the other thing. In general, if we've got 1 of one thing and 4 of something else, that singleton goes in the middle. So phosphorus in the middle, oxygen, 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 oxygen. 8 bonds, 4 bonds, 8 shared electrons. Well, that's easy so far. Now we have to figure out how many unshared electrons there are. Okay. They're sharing, they come in with 32 and they're sharing 8. So 24. Yes. Sometimes it's the simple arithmetic that really trips me up. So they have 32 valence minus 8 shared, 24 unshared. And we can pretty much figure out what that's going to look like. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Last thing we have to do is what? Bracket and charge. This whole thing is bracketed. This has a 3- charge. These are actually really easy once you know how to apply the math. The key step is what I did in red up there. Remembering to add extra electrons if they have extra electrons, because you have to account for those when you're accounting for the total number of electrons that they come in with. Let's do one more together. I did forget on this one to do that important last step check of checking octet to make sure that everybody's satisfied. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Those are all satisfied. And here, 2, 4, 6, 8, and 2. So those are all satisfied. How many of you got that one perfectly? Okay. And my dots are really messy. I apologize. They don't look much like pairs to me. There, we'll move that. You got it? Do you want to do one more polyatomic ion together? Okay. Okay, that's a carbonate ion. It's one that you'll get real familiar with when we start doing compounds with polyatomic ions. Start doing the math. Okay, I got the number of bonds figured out. I got the number of bonds figured out. I got the number of unshared electrons figured out, 16. So I got 4 bonds. What does that mean I have to do somewhere? Double bond. Okay, well, what the heck? Why not here? 1, 2, 3, 4. Where do my unshareds go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I put my charge out here, 2 minus. Am I done? Does something in my tone of voice tell you that there's a trick here and you're not done? Good! Good, you're picking up on subtle cues. What's the trick? What's the trick? So here's my question for you. How do you know the double bond is here? Huh? No, it doesn't. What's the thing we do when we don't know where the double bond exists? We did this early in the week. If there's a double bond that could be in more than one place, we have to do something. Oh, yes, that's it. We have to show resonance. Because in fact, the double bond doesn't just exist there. It exists in sort of multiple places all at once. It's kind of weird quantum stuff. So we have to put a double-headed arrow in between, and we have to represent this whole thing with the double bond in each possible location. Okay, got something that looks like that? Minus my messy cut and pasting. If you do not show resonance for something that requires a resonance structure, it's wrong. You got to show resonance. And the question that usually comes up on these is, how do I know where the unshared electrons go on those oxygens? Because we have a lot of polyatomic ions that have resonance structures, that have a multiple bond between the central atom and an oxygen, because a lot of these are what we call, I didn't do attendance. Okay, so how do I know how many unshared electrons each oxygen gets? I count to 8. All I do. So the oxygen that's double bonded, let's count to 8 here. 2, 4, 6, 8. Oh, it's satisfied. Because it has a double bond, it doesn't have space to take that third pair that we usually see with oxygen, because it's sort of all occupied. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. We're just counting to 8 again and again and again. So right now I'm going to turn you loose. I want you to try the 3 polyatomic ions that are on your practice sheet. Show the gooch math, and I'm going to float around and try to help. Okay, so we've talked about ionic bonding. We've talked about covalent bonding. We've now talked about polyatomic ions, which are this weird hybrid. There's one more thing I want to talk about today, and that, my friend, is heavy metal. So now we're going to talk about metallic bonding. And this gets to the question somebody asked last week about how do you figure out how many valence electrons there are in the D block? Well, it's not that easy. So we get into the D block, and imagine yourself staying all by yourself in a hotel with 100 rooms and only 1 or 2 guests. Would you sleep in the same room every night? I wouldn't. Let's see what this one's like. Ooh. Woo, look! This one has striped wallpaper. Woohoo! Let's keep moving. That's kind of what happens in the D block. You've got, 1 or 2 or 3 electrons in these d orbitals, which are the highest. They're the highest energy, though not the highest main level. It all gets kind of weird. So there's lots of empty room up there. And what happens is those electrons do what we call delocalizing. They float around, they roam, they travel. What that forms is what's often referred to as the sea of electrons. And so what you get is something fairly special. And I'm going to draw this. So I'm going to draw my little positive metallic nuclei, and this could be iron or copper or zinc or anything else. And floating all around it are all these little electrons. It is really like a sea of electrons. And it's not the kind of neat arrangement that we saw in ionic solids like salt. It's a little more chaotic than that. And what you get is a situation where the lines of attractive force, try to pick one more color here, sort of extend in all directions. Well, what does that do for you? It does a couple of things. I have some nice what's called mossy zinc right here. All my hammers were taken downstairs. But even without a hammer, I think I can do this. Whoops, well, maybe. Hey, there we go. Yeah, hammer works better for sure. Okay, so typically, what I can do with a hammer is I can flatten those suckers. I can smash them flat. They're these nice lumpy pieces of zinc, and I can make them nice and flat. I could really, if I was careful and I warmed them up, I could probably smash them into sheets. Because what are the properties that we're aware of metals? Did I hear somebody say malleable? Malleability is the ability to be pressed into sheets, which we do with metals all the time. I could pull out my aluminum foil, but that would require jumping over a desk or something. Because those lines of force extend in all directions, it makes metals incredibly malleable. This is metallic bonding, and it's responsible for all the characteristics we see in metals. So it also allows them to be good conductors, because what do you got? Well, you got, whoops, that's the same one. You got a bunch of electrons that are free to move around the whole compound. So those electrons, you add electrons to a piece of metal, that's fine, we can take more, we'll just push some off the other end. They conduct very well. The malleability and ductility are all because of that sea of electrons model. The fact that there are lines of force appearing, going in all directions. So it doesn't matter if you smash it flat, it's still attracted to itself. Let's contrast that with an ionic compound. Here's my big chunk of salt, and I'm actually going to shrink this down a little bit. Doceri is a wonder. So here's my big chunk of salt, and when I take a hammer, here's a big mallet of some sort that I'm going to hit that chunk of salt with. So when I hit this with that same big hammer and I smash it, I don't disrupt the lines of force. They're running in every direction. They can move around, and every piece is still attracted to every other piece. We have a lot of extra electrons floating around, and they're all attracted to all the protons. So we have really pretty strong forces, so we see high melting points, and we have this malleability. When I hit an ionic compound, what happens? Well, what happens if I shift everything down one? What happens all of a sudden? Instead of forces of attraction, I now have a force of repulsion. Look at that. I've got sodium, sodium, chlorine, chlorine, sodium, sodium. This whole piece is going to split off. Ionic compounds tend to be brittle. You hit my beautiful chunk of salt with a hammer, it's just going to split right along the fracture lines in the crystal. Metallic compounds don't do that, and it's down to how their electrons are arranged. Okay. The next place we would go, normally, would be molecular geometry. We start molecular geometry on Monday.